and welcome to Code Disclosed. In this video, I will explain the idea behind Maclaurin series, how to calculate the terms of this series, and then how to code it using MATLAB. So let's start. In the previous video, we explained the idea behind Taylor series or Taylor expansion, and we said that Taylor series of a function is an infinite sum of terms that are expressed in terms of the function derivatives at a single point. The idea behind Taylor series was introduced by Brooke Taylor, the English mathematician, and since then, Taylor series or Taylor expansion has been an awesome concept, not only in the world of mathematics, but also in optimization theory, function approximation, and machine learning. It's widely applied in numerical computations when estimates of a function's values at different points are required. In math terms, these series or this expansion can be expressed in this form. So it's again, it's an infinite sum of function's derivative. So n here is the order of the function derivative from 0 to infinity at a single point, which is a here. Now, so if you can write these or expand these terms, so for n equals 0, we evaluate a given function at this single point, which is a. And then when n is 1, you just take the first derivative of this function divided by 1 factorial here, times x minus this single point. For n equals 2, we do exactly the same, but this time we take the second derivative and then we divide by 2 factorial times x minus a squared plus infinity. So it's an infinite sum of these terms. We just go higher in derivative and then we go higher by factorial here, and then we go higher by the order of x minus a. At the same time of Brooke Taylor, so this is just a recap of last video. But then at the same time, when this series was introduced by Brooke Taylor, a Scottish mathematician called Colin Maclaurin just introduced the idea: what if we use these Taylor series or this Taylor expansion, but instead of using a single point that is not 0, what if we approximate a given function at 0? So what if we just put a here is just 0? What would happen? Well, actually, the thing that would happen is a new series, not a completely new. It's just Taylor series, but in a special case where a is 0. In this case here, we just write exactly the same thing as Taylor series. But instead of a here, we just put 0. So we evaluate for n equals 0, we evaluate the given function at 0, plus, and then we calculate the first derivative divided by 1 factorial times x here. There is no x minus a at this point. And then we go higher by the derivative and by the order of x to infinity. So it's exactly the same thing, exactly the same Taylor series, but instead of evaluating the function at a given point, we evaluate the function at 0. All right, so let's give an example just to elaborate this idea. So this example or this function, we used this function in the previous video, but we'll use this function now to find an approximate using Maclaurin series. So this is Maclaurin series here, and this is the function x cubed minus 10x squared plus 6, and we want to find approximate for this function at 0, at this point here. All right, let's write the terms of Maclaurin series. So this is the first term. We evaluate f or the function at 0, and then this is the second term, third term, fourth term, and to infinity. Now, realistically speaking, we can't go to infinity. Evaluating these terms, we need to truncate this series at some point. So let's decide to truncate this series at 1, 2, 3, 4 terms. But this time we don't have an equal. It's not equal, it's an approximate. So we need to use an approximate sign instead of an equal here. All right, so let's evaluate each term, and then we can add all of these together, and then we can ask a question: have we reached an approximate, a reasonable approximate for this function? All right, let's start with maybe first term. So the first term is just f0, so we need to evaluate our function at 0. So instead of x, each x, we just put 0 here, and we just end up with 6. So let's put 6 back into the series. So this is our first term here, just put 6. Let's ask the question, what if we truncate this series at the first term? You just keep the first term. Will we get just an approximate function to our actual function? Let's plot it. Well, this is the plot. 6 is just a line as this. It's just a constant. So this is ms1, which is the Maclaurin series, the first term of the Maclaurin series, which is way far from the actual function. So we need an additional term. So let's calculate the second term, this one. For this one, we need to evaluate this function at 0. So instead of a here, we need to evaluate it at 0. But let's calculate the first derivative first. So this is the function, and if we take the first derivative, it will be 3x squared minus 20x. And let's evaluate this at 0. So instead of each x, let's put 0 instead. So this will end up with 0. All right, let's put this 0. So this 0 is the value of only this bit here. So we need to put 0 over 1 factorial times x, which will end up with 0. All right, so I don't think this would change anything with, even if we add these two terms together, we are still way far from getting a reasonable approximation for the function. We need an additional term. So let's go to the third term now, and third term requires us to calculate the second derivative of the function. Now, the second derivative of the function is 6x minus 20 now, and if we evaluate this at 0, we will end up with minus 20 here. So again, this minus 20 is just the value of this bit here, so we need to put minus 20 over 2 factorial times x squared. Let's put this back into Maclaurin series. So this is the bit here, so we have 3 terms now. Let's ask the question, if we add up all of these 3 terms, will we get a reasonable approximate for our function? If we plot this, we will get something like this. So we are close somehow, but still, we can get better. We can get a better approximate for this one. So let's add the final term, and then we can ask this question again. So this term, we need to calculate the third derivative of the function. So we do exactly the same thing. We calculate the third derivative, which is 6 here, just a constant. So if we want to evaluate it at 0, it will stay the same. So this 6 is this bit here, the third derivative. So it's 6 over 3 factorial times x cubed. Let's put it back into the series. So this is the third. This is the fourth term, which includes the third derivative. So we have 4 terms now. Let's add all of these together and let's plot it, and let's ask the question, would that be a reasonable approximate? So plotting it, it will be this magenta dashed line over the function, which is very, very close. So I can say now that these 4 terms would give us a very reasonable approximation for our function. Now, interestingly here, a very interesting thing here, if you just do a very simple simplification for this. So here 2 factorial is 2, so 20 over 2 is just 10, and 3 factorial here is 6, so 6 over 6 is just 1. And you just do very simple simplification for these terms. You can just by comparing the output or the result of these series with the actual function, you can just say, you just can see here that it is the actual function itself. So it is not approximate anymore, and it's not an approximation anymore, it's an equal sign for the function. So that's really interesting. All right, the question here is, how can we code this? How can we code these steps? So let's go to MATLAB now, and let's do these steps or calculate this approximation, or in our case, the function itself using Maclaurin series. All right, so very first step, as usual, we need to start with clear all, close all, and CLC in MATLAB. The first one will clear any previously assigned variables in MATLAB. Close all will close any previously opened plots or figures. And CLC will clear up all of your command window here, just to declutter your coding environment. So let's start first by defining the spatial variable that we are going to use. So in this case, we're going to use the x here, which is line space from -10 to 10, and I will include just 100 points between these -10 and 10. Second step, I need to define my function. So define the function that I want to approximate, which I will call it fx. So fx here is x cubed minus 10 times x squared, and then I have plus 6. This is my function. And now, before anything else, let's visualize the function. Let's see how the function would look like. So figure here, and then I want to plot x and f of x, and let's use the C on here exactly the same color as we used in the PowerPoint. So let's run this and see how would this look like. So this is my function here. And this is the x here, and this is the value of the fx. Let's add actually x label, and which is x, and let's add a y label as well, which is my f of x. All right, now this is my function. Now let's run that again to see the function. So this is the x and the y-axis and the x-axis labels. All right, let's start now by calculate the series of the Maclaurin series terms. Let's start with the first one. So ms, I will say 1. So this is the first term of the Maclaurin series. If you remember, it was 6. It's just a constant. But to plot it, we need a vector that MATLAB can understand how to plot it. If you just put 6, it will give you just 1 point. If you want to see it throughout your domain, throughout from -10 to 10, you need to times it or multiply it by a vector that it has only ones, and it has the range of the size of your fx2, which is the size of your domain. This is the first term. The second term, if you remember, it was 0. So I'm going to do exactly the same thing. I'm going to do 0 and times 1 size of your fx2. This way, MATLAB will understand how to plot just 1 point, which is 6, or just one value. The third term was, if you remember, it was -10 times x squared. So since there is an x here, that's totally fine. You don't need to multiply the ones vector here. The last term, which is ms4, the fourth term of the Maclaurin series, if you remember, it was x cubed here. And the approximate function, it should be the sum of all of these terms. So it's all of these, the sum of all of these Maclaurin terms. Okay, so let's plot the terms. the Maclaurin terms. So we need to plot these terms above the actual function. So let's add a hold on here, so we can plot all of these together. All right, so first let's plot the first one, the first term of the Maclaurin series, and let's follow actually the same code, the same color code that we use in the PowerPoint. So the first term is it's red, and the sum of the first two terms, let's put it as green, and then x, and then ms1 plus ms2 plus ms3, I'm gonna put it as yellow here, and then the last one, which is the approximate actually, the approximate, which is the sum of all of these terms, all of these four terms, and I'm gonna use it as magenta here. Just to make it more self-explanatory, I need to add a legend here. So the legend first is my fx. So fx is my function, and the first one is ms1, which is one term of the Maclaurin series, and the second one will be ms1 plus ms2, which is two terms. And then I need to add, so the third one would be ms1 plus ms2 plus ms3, and then these are three terms. And then the last one, let's put it as the second line. So here we have an approximation, which is four terms, the add of four terms. All right, hopefully there will be no complaints by MATLAB. So let's run this and see how it goes, and how. All right, so let's make this one bigger. So f of x, you can't see it. Okay, let's maybe let's do all of these as dashed, because we can't see the actual function. Okay, let's run that again. So these will be dashed lines instead of the actual solid line. So you can see here the cyan is the actual function. The green here is the first two terms. The red is above it, actually, exactly above it, so you can't see it here. And the yellow here is the first three the first three terms, and the dashed magenta here is the actual approximation. Well, actually, it's not approximation; it's exactly the same function after we did the Maclaurin series. All right. All right, I think that's pretty much it for this video. Hope I will add down in the description box below. If you have another way of coding this, please let me know in the comment section. And also, I will add the link for the GitHub website, so you can use this code and build upon it. Thank you very much, and I'll see you in the next video.